Okay, what we will look at today is something called the time response specifications. So, last time what we had done was, given a first order or a second order system, we just saw how it responds to different kinds of signals, and in the first order system we saw there was something called a steady state error. We will formalize that in a better way today. Second order systems, we saw how the response of the system varies with changing in the damping term, where we saw for underdamped system your response is just continuous oscillations till you have critically damped systems to overdamped systems and so on. So, what we will see now is, given some design specifications, what is the impact of the time response. So, loosely speaking, if I say that I would want to go from, say, some signal, say y of t, I want it to take some value of, say, y equal to 1, right, somewhere here. So, ideally what if I would want to design a system, I would want this guy to go instantaneously to this point at just, say, t equal to 0 plus, that I switch on my air conditioner and immediately my temperature goes to the desired 24 degrees or 21 degrees. Okay. Sometimes it might be difficult to do it instantaneously, but it could be possible to do it a little, something like this, right, or something like this, right. Okay. So, not exactly like this, but we could go in this time or this time. But what I would expect is, if I want to run from this point till this point and do very fast, then I just cannot stop here, right. I have to go a little further, right, before then I again come back and I run a little faster, then I go here, here, here and so on, right. However, if I would not want this thing to happen, I would have to run a little slowly, right, so that I just go here and stop, right. So, these are the kind of behavior we will analyze, is to do with how fast can my system respond, or how fast can it reach the desired value. But if it runs very fast, are there any overshoots, and if there is any overshoot, is there a limit on the overshoot, or can I really say what is the value of y at this point given this guy to be 1, right, or if when does it really reach the desired value, right, and so on. That is what we will try to quantify in this lecture. So, and we will restrict ourselves to the step response of the system, and the analysis becomes much easier, and it is also quite intuitive too. So, in general, all these specifications of how fast I go, how fast I settle down are a part of the design specification. So, if someone gives me a problem, would say, okay, design me something which reaches the steady state value in so and so time, that it should not overshoot beyond a certain limit, say this could be just 0.1, and I would say I would not want to overshoot 1.1, right, for example. And these indices answer the following question. So, based on this arguments, what are we interested in is how fast the system moves to a given input. Is the response oscillatory, and how oscillatory is the response, which is again we know that it is depending on the damping, that underdamped systems will have an oscillatory response, and how fast does it reach the final value, right. Okay. So, here we will restrict ourselves to underdamped systems, right, and we will focus on the step response or the unit step response. So, to quantify this, we will define for ourselves few things, right. First is the delay time, the time required for the response to reach 50% of the final value at the first instance, right, and I could calculate this based on the formula which I had derived earlier. Okay, I'll come to this. We just first define what these are and then go to see how these numbers are achieved. So, the delay time is a time required for the response to reach 50% of the final value at the first instance. You could have that in an oscillatory response, that it could reach the 50% several times. The rise time is usually defined as the response to rise from 10% to 90% of the final value for overdamped systems, and since we are here looking at underdamped systems, we will look at what time does it reach the peak, the desired value the first time, or from 0 to 100% of final value at the first instance. For example, if I just were to plot it, so this till this, and I say this is my desired value, these things, right. So, here, well, this is what is called as the rise time, right. So, where it reaches the value of 1 the first time. You see that it reaches value here of 1 here, here, and so on. It keeps on oscillating until it settles down to its final value. The delay time is this time, right. So, this is a TD where my response takes the value of 0.5. So, this is my time, this is my response y of t. Okay. Similarly, the peak time is the time required for the response to reach the peak value. So, somewhere here, right. So, this is my peak time. Okay. Then I will also quantify, if I reach a peak, if I am going from the desired value to some other value, how much is this overshoot, right. So, this is quantified or called as the peak overshoot, and this is just computed as the percentage of overshoot, like. So, this is how much I deviate from the steady state value at the first instance. So, the YTP, which is what I overshoot here, this one, this is the value of y at TP minus the steady state value, and then you just calculate that it in percentage of deviation from the steady state value. The settling time, so we had vaguely defined this last time when we were dealing with first order systems, and we will recall that all over again. The settling time was defined as a time required for the response to reach and stay within a specified tolerance band. So, usually I would say, well, the system has reached some kind of a steady state value if it is within 2% of its final value, sometimes even 5% depending on my tolerance levels. So, if I, in this case where the steady state value is 1, I would say the settling time is when it reaches to 0.98, right. Okay. So, again all these things. So, settling time, we said, we thought, or we had derived the settling time concept earlier for first order system, right. So, and these concepts, the peak time and the peak overshoot are not defined for overdamped and critically damped systems. That is because, okay, let us start with the response of, so this is the underdamped response. The critically damped response would be something like this, right. It will never cross this value of 1 or the desired value. This is the critically damped system. So, this is the underdamped system. This is underdamped, this is critically damped. So, TP and MP are typically defined only for underdamped systems, and that is what we will focus most of our analysis on. Okay. So, this is what it looks like, right. So, a typical response of a first order system, this we derived last time, it looks like this, it is like has some kind of damped oscillations, right. So, again I have the delay time, the rise time, the peak time, and the settling time, right. So, the first time when it reaches this guy. So, this could be within 2%, could be 0.98 or even 1.02, but once it is here, it always remains within the 2% value, right. It will never go down below 0.98 because the oscillations are continuously being damped. So, these are the values which we will focus on: TP, TR, MP, and all this settling time. Now, the idea would be, can I quantify this based on my system parameters, right. So, start with the second order undamped system with transfer function which we had derived, which we had said last time was as a typical transfer function, if I could call it G of S, was omega n square over S square plus 2 zeta omega n S plus omega n square. And the response of this system, and I will do this, zeta is less than 1 and of course greater than 0, right. So, the rise time, so this system subject to a step input had a solution like this, and we derived it last time, right, with T not replaced by TR, right. So, this TR is the reason we have TR is, okay. So, the rise time is the time taken by the step response to go from 0 to 100%. So, this is the 100%, this is the solution of the equation, and I want to calculate the time t at which it reaches this value of 1. okay, and therefore I replace this T by Tr in the solution to that equation. So, okay, so I do this, the 1 and 1 goes away, so I am left with sin omega d. This is the damped natural frequency, if you remember, was related to the undamped frequency in this way. Okay, this was omega d. Okay, so when this goes to 0 for the first time, so which means omega d times Tr plus theta equal to pi, or Tr is just this one, pi minus theta over omega d. And what was theta? So theta, okay, yes, it's written here. Theta is cos inverse of zeta from the damping coefficient, right? Okay, and then this relation between omega d and omega n, the damped natural frequency with the natural frequency of the system. Okay, similarly, I can calculate the peak time is the time taken by the step response to reach its peak value. Okay, now how do I find what is the time? Right, so if I am here, I am looking at this value, right. So this is a function. If I just, so y is a function of t, so it starts here, it goes here, and again comes down, right. So this is the maximum value that the function can take, and from calculus I know that the maxima can be computed by taking the derivative of y, right, and then setting this to 0. Essentially means I take dy by dt, I set it to 0, and I compute the time at which this happens, right, the time over here. Okay. So I do all these computations. So I take the derivative of this, so this 1 disappears, and I have is this one, 0 is all these guys, and then I solve this step by step to get this value, that omega d times Tp is this one, and therefore again I am just interested in the first instance, right. So this is one peak, and then dy by dt would go to 0 here, dy by dt could go to 0, at several points, right, here and so on. But I am interested only in the first time, right. This is the value which I would be interested in, right. So this Tp would be simply pi over omega d. Okay. So how do I express this overshoot as a percentage, right. So I calculate the peak value, and then the steady state value is 1, the desired steady state value, and here in this case it will just be MP would be Tp minus 1, right. So how much I overshoot from here, this number from here till here. Okay. Okay, so I can just substitute y of Tp here, and I just y of Tp would be just, I know the value of Tp, that this is pi over omega d, I plug it into the solution, okay, which the solution over here, and I just see how much it deviates from the steady state value of 1. So y Tp, substitute for Tp in the solution of y of t, and this with all these computations would be something like this. So Mp is e power blah blah blah, and then this term gets cancelled because of cos of theta, if you see here, is defined this way, right. Sorry, theta is cos inverse of zeta, theta is cos inverse of zeta, or cos of theta is zeta, and then I just use sin square theta plus cos square theta equal to 1, and these guys just disappear. So the peak overshoot in percentage is E to the power, this guy. Okay, some properties of this one, right. So if I say, well, what are the limiting cases here, right. So we go from say zeta equal to 0 when there is no damping, what we would expect is that MP would be the highest. Okay. So if my steady state value is 1, then MP here would be, okay, substitute for zeta is 0, 0, and so MP would be 1, okay, which means my peak overshoot would go from, this is the value 0 to 1, this is the desired value, it will go all the way till 2 and then come back and just keep oscillating like this. That is the standard response which we saw. It is almost it's like 100% overshoot. Okay. Now if zeta keeps on increasing, I see that my overshoot keeps on decreasing. right. So, if I just were to plot the peak overshoot versus zeta, the zeta going from 0 to 1, and see that this will go from 1 and all the way till 0. Okay. This is really important, right. So, one of the design parameters here could be, if I were to restrict my peak overshoot, then my problem would be to have to design my system with the appropriate zeta. Okay. So, similarly for settling time, the settling time is a time required for the response to reach and stay within, say, a 2% band of its final value. Okay. Okay, so how do we compute this? So, okay, let us say do some pictures here that, okay, I am here and my response is again something like this, right, and this is my steady state value. Let us say this is 1. Okay. Okay, maybe I have to go a little further up here. Okay. So, if I look at this response here, you can see it is actually bounded from below by a curve like this and bounded from above by another curve like this. Okay. Now, what are these curves? These are simply these exponential curves here. The guy on the top would be 1 plus e power minus zeta omega n t. Okay. So, this r would just go over here. This will just be the standard t. Okay. Over square root of 1 minus zeta square. So, this is the curve on the top and this is the curve on the bottom. This is 1 minus e power minus zeta omega n t over square root of 1 minus zeta square. Okay. And then, so this value here would be 1 minus 1 over square root of 1 minus zeta square, and the value here would be 1 plus 1 over square root of 1 minus zeta square. Okay. So, this is all good, right. So, if I say, well, when does this curve inside the solid line reaches within 98% and stays there? Well, the answer could be that whenever this curves, you know, this guy, whenever these reach the within the 98% and then stay there, because these are enveloped by these curves. Right? The guy on the solid line is just enveloped by these two curves. So, I can just now look at the response of this system, right. So, I am just say, okay, let us take the bottom one here, for example, 1 minus e power minus zeta omega n t over square root of 1 minus zeta square. Okay. And this, if you remember, this looks like the response of a first order system, right, where we had the other day that the response was 1 minus e power minus t over tau, right. And if you just look at that response, we had some things defined like this. Okay, this was my 1, this was my response y of t, and this kind of looks similar, right. So, this is a time constant of t, this is a time constant 1 over zeta omega n, and with t, so this guy reaches at the first time constant, it reaches the value of 63%, okay, and then at t equal to 2 times the it reaches some value of 0.8, right, and then at t equal to 3t it reaches 95%, and at t equal to 4 times the time constant it reaches 98.2%, right, somewhere here. And this we had done this last time. This is 2 times t, this is 3 times t, this is 4 times t. Okay. Now, if this guy reaches settling time at 4 times the time constant, this guy would also be reaching in the same time, right, because this is just enveloped by this by the curves there, right. So, now my settling time can be defined directly in terms of the time constant, right. This is for the 2% tolerance band and settling time Ts, and then Ts would be 3 times the settling time when I am at the 5% tolerance band. Okay. So, how do I write this? So, Ts, so if I again look at my curve, the time constant there was, so I just take the bottom curve, 1 minus e power minus zeta omega n t over 1 minus zeta square. So, this has a time constant of 1 over zeta omega n, and therefore, my settling time would just be 4 times the time constant, will be 4 over zeta omega n, or the settling time, this is for the 2% criterion, and this would be 3 over zeta omega n for the 5% criterion. Okay. So, what does this mean? That the settling time is inversely proportional to zeta and omega n. Again, let us say the limiting case, let us say the limiting case of zeta being 0, my settling time would be infinity. This is not surprising, because if my settling time is infinity or when zeta is 0, I am just having like an oscillatory response, right. My system will never go anywhere within the 2% or even the 5% or even the 50%, right. So, settling time would be infinity. So, as zeta increases, your settling time tends to reduce, right. So, based on this formula here, zeta increases and then the settling time reduces. So, okay, I do not want to draw a graph for that at the moment, but we will just understand that the increase in zeta will cause a reduction in the settling time. Okay, now what is that sufficient to increase zeta? Okay, so my peak overshoot is also some function of zeta, okay, in such a way that if I have a smaller zeta, I have a smaller peak time or then even a smaller rise time, right. So, if I want a faster response, my zeta is smaller, but then my overshoot will be larger, right. So, usually in the design specifications, my peak overshoot would be specified and my zeta would be calculated based on the peak overshoot. And therefore, if I were to look at settling time, it just depends on the natural frequency of the system. So, to adjust settling time, I can play around with this guy omega n, right, omega n also over here, because zeta is already defined by the performance specifications of the peak overshoot. Okay. So, when this is fixed, I may not be able to change it here again, because a smaller zeta would maybe increase in a bigger overshoot, which may not be very desirable. Okay. So, I can just play around with this omega n, and slowly we will see how we could smartly design these things so that I have not a big overshoot, but also a smaller settling time and so on. So, ideally what we would like is to have faster response and a smaller settling time. Okay. So, what could be application of damped or this several kind of systems, right. So, let us start with overdamped systems. So, this is push button water tap shut off valve. So, just before we started this recording, my student was telling me a nice analogy of this, right. So, originally if you look at the trains, the taps in the train, we would have normal taps which people would just forget to turn off, and then we could waste water. Then later on they had these things, I do not know if I could draw a picture of this, right. So, like this, and then you will have a tap and then the water flows through here, right, and then you keep on pressing this, and then once you release this, the water will not come anymore, right. So, what they do now is that you just press it, so the system will give us water for some time and eventually the valve will close. That is like the example of an underdamped system. Like the emergence in technology can be seen when you travel by train, right. I do not know if the trains still have this kind of smart things or not, but this is in more sophisticated thing, you have this sensor, you just put the hand and then it just actuates this, and then the water just the valve just closes off gradually. Same thing you can see in this automatic door closers, right. They can't really have a fast response and then bang on to the wall or to the stopper, right. So, these are automatic door closers are also typically overdamped systems. Critically damped systems, you would want them to have an elevator mechanisms or even gun mechanisms, right. So, you want the elevator to have a faster response, but you would not want it to overshoot. So, we talked of this last time as well. And of course, underdamped systems, all string instruments would do that, because if you pluck a string, say I have a guitar, I pluck the string, and usually it has this nice wave kind of formation, right. But if you plug the string from here, it goes here and again comes back here, it may not generate the sound which you want, right. Similarly, all electrical or mechanical measuring instruments, right. So, you take a voltmeter, if it were to measure via a scale like this. So, if this is a 0 position, it will typically go to the desired value and then come back, right. These are usually underdamped systems, right. All this moving coil or moving iron measuring instruments. Okay. So, once we do these things, we are also interested, does my output follow the reference all the time. So, we saw last time when we were doing the response for a first order system, in some cases we saw that there is a steady state error, which means the reference is not tracked directly by the output, but it is with some error which was defined by the time constant, right. Okay. So, let us try to formalize that a little more and then we will revisit the original examples which we had. So, the steady state error, so a typical feedback loop looks like this. You have the reference signal, the output, the feedback loop, and the difference between the reference and the output is termed as the error signal, and this error I would typically want to go to 0. Now, given these characteristics of the system, the G and this 1, it will also be H, nothing would change in the analysis. So, given this G, can I find what is the error, right, depending on the nature of the signal here. Okay. So, what is the steady state error? It is the error between the actual output and the desired output as time goes to infinity, right. So, we know from final value theorem, if I call this signal as E of t, that ESS is limit s going to 0 s times E of s in the Laplacian domain. Okay. Now, this E is r minus y, and y I know is, so this transfer function here is g of s over 1 plus g of s. Okay. So, this y given this r, so I can write this as r minus g times r over 1 over g, and I get this one. Okay. So, this is my error signal. So, in this thing, the steady state error, the limit s going to 0 s times E of s would be limit s going to 0 s times r plus 1 plus g. Okay. Now, this will make use of this little thing here, and it will give us lots of information of the system subject to several inputs. Okay. So, let us start with a step input, right. So, this will be fixed all the time. Okay. So, for the step input, r of s is 1 over s, and what is the steady state error? ESS is limit s going to 0 s times r of s, and this r of s is 1 over s, right. Okay. So, this s and s disappear and I am left with this. So, this limit would be 1 over 1 plus Kp, right. So, this Kp would be limit s going to 0 g of s, and this limit will always exist because we are looking at causal systems, right. So, well, with this limit will always exist. We do not really care about if this might blow up to infinity or not, right. This this like the DC gain will always exist. So, where Kp is computed as limit s tends to 0 g of s is called the position error constant, right. So, I am just tracking a position, a fixed position 1 over s. Now, similarly, if I go to an input which is a ramp, where I am tracking a ramp. So, this steady state error is, again I do all the computations, one of the s disappears and I am just left with this, this guy goes to 0. Okay, let us compute that. So, I have s limit s going to 0 s 1 over s square 1 plus g s. So, this would be limit s going to 0, one of the s's would disappear and I have 1 over s plus s times g of s. Okay. So, now this would go to 0, this s, and then what I am left with is limit s going to 0 s times g of s, and I call this the kV. So, where kV is limit s going to 0 s times g of s, and I call it the velocity error constant. Okay. So, if I have a feedback loop, I just draw it here again. So, 1 reference plus a minus y of s and so on. Okay. Right. So, if the input or the reference is a step, then there will always be a error. So, the response, so y of s, so if I just take an underdamped okay, whatever kind of system, and if I just look at the steady state curve, so this is my desired value, my actual value might just be somewhere here, right. So, this is the steady state error. Okay. So, we might think of, so if this is the position error, we might sometimes think that the velocity error is actually that error in the velocity, but that is not true. It is just a velocity, it is an error in, it is not the error in the velocity, but error in position due to a ramp input or due to a velocity input. For example, I am maybe chasing a car here, right. This is say a car C1, and then this is my reference car, and then I just want to meet it, right, and at C2 this is my car, right. So, as time goes to infinity, so we are always at say a distance of say 1 meter from this, right. So, this is just error in the position, we are not having an error in the velocity, even though we could just be moving at constant velocities, right. So, this could be some velocity v1, this would also be the same velocity v1, but I will just have a error in the position. Okay. So, it should not be confused with error in the velocity. Similarly, if I were to say, well, give me a temperature of 24 degrees, I just go to 23, the steady state error here is 1, right. So, I am just tracking a position, right, I just want to go to 24. But however, if I say keep on increasing my temperature profile with time in this way, okay. So, say this is, it increases with say 1 times T, okay. This is my T and this is my temperature, the reference temperature, right, with time it just keeps on increasing. So, if I say that the velocity is there is a velocity error, I start from here and I will just be here. So, if this has to increase constantly at T, well, I will always be behind by say 1 degree. Okay. So, at say at some T equal to 50, I might just be at 49, and T equal to 100, I might just be at 99. Okay. So, it is just the difference in the position, not really the rate of my car here or the rate of change of temperature here, right. Okay. Similarly, if I have a parabolic input for which the Laplace transform looks like 1 over S3, I can do all the math and I say that the steady state error is 1 over Ka, with Ka defined in this way, and this guy is called the acceleration error constant, and I just this has an extra S over here, right. Okay. So, the error constants, these 3 things, and these are the standard test signals which we also used in the earlier lecture to study response of systems. So, the error constants Kp, Kv and Kv, they describe the ability of a system to reduce or eliminate steady state errors. For example, if I, okay, we will come to that, right. So, and then these values depend mostly on the type of the system, why this type is important, and as the type becomes higher, more the steady state errors are eliminated. Okay. We will just define this type in the next slide, right. Okay. So, I will come back to this slide okay, a little later, but just the type of a system is defined here by the number of poles at the origin. So, if I have a system in the pole 0 configuration, G of S could be typically some gain with a set of zeros, with a set of poles, and additionally some set of poles at the origin. Okay. So, if there are n poles, I will call it a type n system. If n is 0, I will call it a type 0 system, and so on, right. And we will see how does this type actually now influence the way I compute the steady state error. Okay. So, that is the type of the system. So, the steady state error is a measure of how accurate my system is, right. Does it really track my reference accurately, or is there, so the accuracy should, so in an ideal scenario I would always want it to track it to its desired value, right. However, there could be situations where it may not be possible to do so. In that case, I would like the error to be as small as possible, and that is a very important performance parameter, right. I do not want a desired temperature of 24 and end up at 12 or 31 for example, right. So, this steady state error now depends on 2 factors. right. It is the nature of the signal which I am tracking, and also what is the nature of the physical system or the type of the system, right. And of course, all these things we will only calculate for closed loop systems. Of course, I will calculate for closed loop systems only based on the open loop information. I do not really need to see what is happening within the loop and so on. Okay. So, we will see how we will do that. So, start for a type 0 system. This G of S is again k set of zeros, and there are no poles at origin, right. So, this n in the previous slide, this guy would be 0. So, I will just have these poles. Okay. So, how does it respond to a step signal? Well, for a step signal I have this guy 1 over 1 plus Kp, right. So, that there will always be some constant error, right, at the steady state, right. It can track position signal. For example, this is my position signal. This guy can track, well, possibly I would not say the response, but it could be something like this, and maybe it will go and then there will be some error, right. So, there will be some steady state error here, okay, if I am just tracking this step. Now, this system can never track a velocity signal. Why? Because the steady state error is computed in this way, limit s going to 0, 1 over s times Gs, this is infinity. So, at steady state it will never be able to track a signal which is like this, right. The error will keep on increasing, right. So, this guy, as we keep on moving further, the error will keep on increasing. Similarly, it will also never be able to track a parabolic input. So, the acceleration error will also be infinity. So, to summarize, a type 0 system has a constant position error and infinite velocity and acceleration errors all at steady state. So, all these are related to this steady state behavior. At the moment, I am not worried about what is the peak overshoot, what is the rise time and so on. I am only interested in what or how my system behaves at the steady state. Okay, type 1 system, well, I just do all the computations again. I have one limit s going to 0, 1 plus Gs, and since this has a pole at 0, this guy will go to infinity, right, the Kp. So, okay, let us again go back to see how we had defined Kp. Kp was defined at limit s going to 0, G times s. Okay, so this guy, since s has a pole at the origin, this will go to infinity and the error will go to 0. Okay. Similarly, the velocity error would be limit s going to 0, 1 over s times g of s. So, this s and this s would cancel out and I will have a constant here, okay, and the acceleration error will go to infinity. So, if I take a type 1 system and I ask it to follow a step input, then it will at steady state there will be no error, it will actually follow this input very nicely. Okay. However, if I take the same system, I ask it to follow a ramp, it might have some steady state error, right. It might just go, the response could be something like this and eventually go to a constant error here, like a straight line. Okay. And similarly, acceleration, it will never be able to track a signal which is parabolic. So, it will have a 0 position error, a constant velocity error and infinite acceleration error at steady state. Okay. Now, type 2 systems, right. So, nothing will change here, the position error will still be 0 because I have this s in the denominator, I put it to 0, g of s goes to infinity and 1 over infinity goes to 0. Similarly, the velocity error, so I do s times gs, one s still remains in my denominator, so this will still be 1 over infinity and the velocity error goes to 0. However, my acceleration error constant now has some number here, it was infinity in the previous 2 cases. So, I could summarize by saying that if I take a type 2 system, I ask it to track a position or a step, it will track it perfectly, right. There will be no steady state error. If I ask it to track a ramp, it will also do it perfectly. If I ask it to track a parabolic signal, it will do it, but there will actually be a small error determined by this acceleration error constant. Okay. Now, we see that if I say give a little problem saying take a type 0 system and make the position error to be 0. what would I do? I will just say, okay, this looks, remember all this theory now, and I say just put an integrator, right, or add a pole at the origin. I can always do, this is a system which has more poles than zeros, I can possibly always realize this, and I can just put it here, right. So, this is, can this be done, can this not be done, or can this be done with some being a little careful, we will see all those things. But these are the design specifications which would be given to us, and then we can see that these errors can be quantified just based on the type of signals which we are tracking and the type of the system. So, having an integrator in my system or having a pole at the origin gives a little more hope to me in designing the system. Okay. So, in this entire module, what we started with block diagram representation, signal flow graphs, and then reducing the complexity or finding the transfer function by reducing the complexity of the block diagram, or simply using the signal flow graph formula to find the transfer function. Then we also saw the time response of first and second order systems with standard inputs, and we also justified why we were using these standard test inputs, because in real time we can see all these signals. The real time signals could be a combination of all these test signals. And then we actually quantified our performance in terms of the steady state error, in terms of how much do I overshoot, what is the rise time, and so on, and we had explicit formulas for those, right. And in the next lecture we will, and so far what we assume that the system is stable, right, and we had a very crude version of the definition of stability, saying if it starts with 0 initial conditions, it should come back to its original configuration. So, we will have notions of, define these notions formally of stable and unstable systems, and see how can we define these things directly by the transfer function looking at the poles and zeros. Just by looking at the poles and zeros, can I say if the system is stable or not, or another notions where what is called as the bounded input, bounded output stability. And then given a transfer function of fairly complex level which has lots of poles and zeros, I will just teach you how we use the Routh-Hurwitz criterion for the stability of to determine these systems are stable or not. Okay, thank you.